class. This is Miss Green, and here we're going to look at topic 5.3. We're going to graph some radical functions. We want to be able to graph radical functions, which includes the square roots and the cubic roots, and then we're going to look at some key features when we transform these functions. Remember, the key features would be domain, range, things like that. We've done that with other functions, and now we're going to do it with radical functions. And the essential question is, how are we going to use what we know about transformations to graph the radical functions? These look a little different. It has still the same basic guide that we've used before in the past. So when we have an nth root of something, so it could be a cubic, a square root, whatever we have out in front will cause either a vertical stretch or compression. And you remember the stretch is when a is greater than 1 and it stretches, goes higher from where it was initially. And then a compression would be a would be less than 1 but greater than 0. And if we have a negative sign in front, we're going to do some reflection. Sorry, that doesn't look like an R. Now the H here determines a horizontal translation. So if it says x minus h, then we know we're going to the right. If it says x plus h, we're going to the left, assuming h is a positive number. K, when k is positive, we're going up, and when k is negative, we're going down. And if you're ever not quite sure, of course you can just put the point into the equation and see where you end up, or you could graph it and see for yourself on Desmos or on your calculator. Now I did this one on Desmos, and I wanted to look at this example, but before I actually look at the graph, I wanted to say, okay, let me see what this is doing. So this looks like a vertical stretch. And then minus 4 means I'm going to the right 4. And up 2. Now you haven't really looked at these a whole lot, but this is a square root function. This is the function. And a square root, notice, we're going to talk about this in a little bit. To make it a function, I can't do any values here because this point 10 can't have a positive and a negative output. It can only have one output. We'll talk about that in a little bit. Let's look a little bit what I did here. So y equals x squared. That's the red one. That's this one. Y equals x squared. And then I graphed in the calculator. This was in Desmos, but I graphed y equals the square root of x. Remember, that's the same thing as x to the 1/2. And notice it's all positive. And then when I graphed y equals the negative square root of x, then I've got all these negative down here. If I put the positive square root and the negative square root together, and I rotated it a little bit, it would lay right on top of that one. You can kind of think and look and see if you see anything else that looks similar. Looks like this one shares a point. That one's interesting. They all share this point. So there's other things you might notice. Now when we talk about a function, what has to be true about x and y? We can only one output or y value. That's my y value for each input or x value. And that's really important. That's why when we look at this one, when we do y equals the square root, we're only looking at the positive. Because if we looked at the positive and the negative, then we wouldn't have a function anymore. Remember the vertical line test? Intersects here if we put those two together, if we did the positive and the negative. So that's why when we do the square root, we're only doing the positives of that. Let's look at this one a little bit. I went ahead and graphed this one, and I put in a couple points that I found. And I'm going to look at some of the features. So when I look at the domain, that's the x values. So here's my x and here's my y. It looks like I can't get any less than 0, excuse me. So the domain would be, it would include, remember the square bracket, would include 0, but it goes on and on and on and on this way. So it would go to infinity. Now you're going to see in your Math Excel assignments, they're going to use this set notation a little bit. And I don't know if you remember doing that. X is greater than or equal to 0. That's that set notation for every x such that x is greater than or equal to 0. It says the same thing. A lot of times we just write this part, x greater than or equal to 0. Now the range, that's the y values. Notice this would be my smallest one again. So the range would be 0, but they do go on and on and on and forever and ever. So the range keeps increasing too. And this would be written very similarly, y such that y is greater than or equal to 0. So I'm just kind of helping you out there a little bit for that set notation. Increasing or decreasing? Well, increasing means as the x gets bigger, 3, 12, 27, the y gets bigger, 3, 6, 9. So sure, it's increasing. And you remember the asymptotes we looked at in previous functions? This one doesn't have an asymptote. It's just going to get bigger and bigger and bigger and go to infinity. So there's no asymptote here. Now a cubic root looks a little different. Kind of looks like the cubed function twisted a little bit, right? The cubed function went something like that, right? And we rotated a little bit, and now we've got this, let me erase that. I don't really want that on there. Yeah. Now we've got this function that's kind of sideways, like the square root function. This is the graph. You can make a table too and put numbers in. You want to be, you could do, if you're not careful about what numbers you put in, you're going to get some decimals. Now that's just up to you. It's not really that big of a deal. But here I had a couple values I put on there. But if I put 0 in, I would get 0 out because the cube root is 0. And I put 4 in and negative 4 because when I multiply 4 times 2, I get a perfect cubed, and then I would just get 2 out or negative 2 out. And I did another one here just to get kind of, you're thinking that's a strange number to put in there, but if you do 13.5 and you double it, you get 27 because you're multiplying times 2, and then the cube root of 27 is a perfect 3, and the same would be for the negative. So that's why I chose that one. So the domain on a cubic, well, it looks like it goes on forever, ever, and it does in both directions. There's nothing stopping it. So again, in the set notation, you would have x such that x is the set of, I think it does it like this, all real numbers. I guess it could say, it might do this too. Oops, infinity and greater than negative infinity. It might look like that too. Not sure what Math Excel uses on that one. I have to look. Probably this one. The range would be, again, it goes on and on in both directions, like it's just getting smaller and smaller, more negative, bigger negatives, and these are getting bigger positives for the y values. They'll just keep getting bigger and bigger. It'll take a while, but they'll go forever and ever too. So the y would look just like the x, where you could say y is less than infinity and greater than, I should have written, that works. And again, as the x gets bigger, right, What happens to my y's? Well, they're getting bigger too. So it's increasing. And is there an asymptote? Nope. It'll never approach something and it will always keep going. Too many negatives in that sentence. All right, let's look at this one. I want you to try this. You can either graph it using some points. I'd like you to try that first, but you got to be kind of picky about which points you use. I'll get you started here. I would suggest, notice if I use 0, 1, 2, 3, or 4, I'm going to get a negative, and I can't. That's an imaginary number. So I'm going to start with 5, and then I'm going to give you a little help here on how you can still get perfect squares. Try these numbers. Okay, so stop the video, come back and see what you get. Did it look like this? Hopefully you did. You could also put it in your graphing calculator and try to get some exact points there too. But you can see that it's increasing. There is the domain. So this is, when you looked at it earlier, remember how it said a nth root of x minus h plus k. So what do you have here? H is 5, and that's this point here, 5, 0. This is my h, and this is my k. And then k is 0, right? Just from that. And a would be 1 on this thing. So I'm not stretching it or compressing it. Let's try a cubic one. I want you to try this one. I'll help you again with the points, just to kind of get you started a little bit and get you some points that will give you some perfect cubes. So if you do -9, -2, -1, 0, and 7, and you get any more, you're going to go off the graph anyway. So try those and see what you get when you come back. Something pretty close to this, yeah. Had to do a little stretching out here because of the numbers. Now, the domain and range, again, it's an odd function, right? Well, how should we say it's not really an odd. The cubic root, the 3 is odd. And notice that the domain and range are all real numbers. And it's increasing. And there is no asymptote. There is this point, however, that I didn't really talk about earlier, but we want to make note of it. Whoops. This thing right here is the point where we could reflect, or I guess we could rotate it around this point, and we would get the same function. That's what we would do. We'd rotate it around 180 degrees, and we would get the exact same graph. So that's called a point of symmetry, and we call that's -1, 0. On the regular, it's whatever h and k is, right? So this would be -1, 0. That's your h and your k on that. Here's the general thing that we talked about earlier, and we talked about what causes a stretch, h and k, which way it's moving, and up and k is up and down, and h is left and right. All right, so we're going to now go back to transformations. Like, oh, we haven't done that in a long time, right? So let's look at the transformation, this function right here, 2 square root x plus 3 plus 5. Now what I did here to kind of help you out a little bit is to look at the transformation, I graphed the original, this would be my parent function, y equals the square root of x. I graphed that one here. And then I went ahead and graphed the 2 times the square root of x, because the 2 is greater than 0, so it's causing a vertical stretch. And you can see that pretty easily. See how it's going farther and farther away from this function at that point. So it's stretching it up. Now, because of that 3 and 5, and it's actually, it pointed out here, plus 3 is like a -3, right? So it's -3, 5 would be this point right here. That's my HK. So A is end at 2, H is -3, and K is 5. So this means left 3, and this is up 5. And then I stretched it vertically. All right. So when that happens, you can see if I compared this shape to the red one to the blue one, you can see how that moved. The H was 0, 0, the HK was 0, 0, and now it's negative 3, 5, that point right there. And the domain, right? So I do have a limit on my domain because my X can't get any smaller than that, H right there. So the domain, you could do the set of all x's such that x is greater than or equal to whatever h is, and we decided it was negative 3. Oh, sorry, that's for this one. And for f of x, that's the blue one. That's where x is greater than or equal to 0. Now the range for f of x, same thing. X is greater than or equal to 0. You could do this too. And then the g of x, the range k, that's my 5. So y is greater than or equal to 5. Or you could do 5 to infinity. Or you could use the set notation, y such that y is greater than or equal to 5. So the set notation just does it a little prettier than just saying y is greater than 5. All right, so that gives us an idea of what happens when we transform a graph. So I want you to try this one. I did go out, you can look up here to see what I did. 0.5 would be the same thing as 1/2, right? So it said 1/2 square root of x minus 1, then minus 3. So find the a, the h, and the k, and you can look over here to see which ones I graphed and see if compare when we get done. I guess the biggest thing here that's a little different than the other ones is that we actually compressed it. So right here you can see that my original, and when I just did that 1/2, the square root, you can see how it's shrinking down, right? It's getting closer and closer to the x-axis is what it's doing. And so these two then are just translated from 0, 0 to the 1, negative 3. And then these numbers, the h and the k here, determine my range and domain. Now, this one's a little harder. Oh, actually, it's not. I was just going to show you something. I thought we were going to look at the graph and try to figure out what the graph is, but no, I'm going to show you something that's kind of interesting about if we have something under the radical like this. So we know that that's the same thing as 3 square root of x. So it does something a little different to, we actually, let's go ahead and let's graph these points. So when we put 1 into this equation, we get 3 out. When we put 4 in, we get the square root of 4 is 2, 2 times 3 is 6. And when we put 9 in, the square root of 3 is 9. We'll get 9 out. So the graph is going to look a little different, right? Let's go ahead and look at 1, 3, 4, 6 would be up here. And then we have 9, 9. All right, so we've got those points. Now, when we have this A outside, we call that a vertical stretch, because sure enough, look what's happening here. Yep, they're getting higher and higher and higher. So this is 9, 3, and this one is 9, 9. This one is 4, 4, 2, And this one is 4, 6. This one is 1, 3. Oh, so 1, 1, sorry. And this one is 1, 3. All right. Now, if we left it underneath and we looked at when the y values were the same, and this is the part that's a little different. We're not going to do overkill on this, but just to see. Here's a y value and here's a y value. What happens to the x? Well, we actually got closer to the y-axis, didn't we? We started here and we went this way. So this can be one of two things. You can call this, especially when it's underneath, we would call that a horizontal compression. But when we pull it outside, we call it a vertical stretch. Because here we're looking, what happens to the x's when the y's stay the same? This is what happens to the y's when the x's stay the same. That's the difference between the two, and it's not a huge thing, but it's something I just wanted you to be able to look at. Here's another example, and we want to rewrite these a little bit. Notice this is not in the form x minus h plus k. Notice x has something multiplied it. So we need to get that thing, it's in front of the x, out of there. Well, if we distribute, or if we factor out, then maybe we can do something with that. So 4 times x plus 4, and then the plus 7. All right. But now, remember in the last section, we said we could do that, we could do this. We can separate those two factors and then just add the 7 over here. So that gives us a 2 right here, square root of x plus 4, plus 7. Now it is in this form, more or less. We know that h is a negative 4. So that means it's going to go 4 over in the horizontal direction, and then it's k is a 7, so it's going up 7. Notice they went by 2's here. So this thing right here would be negative 4, 7. And this said, if I wanted to, I could just find some points and graph them. I could do that too. That's another way to do this and get some points to see what the new graph would be. But I could also just say, okay, now what I would do would just take these points and whatever x is, take the square root of it, multiply by 2, and add 7. So notice I have here, that would be a vertical stretch. So that would be a stretch if this one were lined up right here. You could see that it would go up vertically each time. So that would cause that vertical stretch. I want you to just look at the first one to start with, and then tomorrow we'll do the second one as a warm-up. So I want you to try that first one and see what you come up with. What transformations of the parent graph produce the following? So think about what it would take. You got to remember, you have to get it in the form where you have an a here, and then you would have x minus h plus k. So do a little figuring and see what you come up with. Here, and again, you could graph it. I do want to point out that since the square root of 7 is greater than 1, there is a stretch in the horizontal direction because I pulled it outside. And that's when I can divide this here. And you could use an approximate if you wanted to. All right, we'll start with that next one because that one actually even has a reflection in it. So that one's going to be a little more interesting. All right, have a great evening.